Okay, so thanks everybody for joining us today in person and on Zoom. Today we have a joint of T&DI and ACI. And we have our very Jordan Ouellet. Since he got here, he's been interested in 3D printing, and he has been using it for his research to build parts for gyro compactors and help research progress. And we all wanted to see how he's doing this and what resources he's using from campus so that we all can get advantage of this too for our research or your research. So welcome, Jordan. And we can
Thank you, Javier. Hopefully it's helpful for everyone. So I just want to make sure the meeting is being recorded. Vikram, this is good. People on Zoom, how's the audio quality? Can I have a thumbs up if it's good? Or maybe in the chat? Chat here. Maybe that's good, perfect. Okay, so if audio is going bad or video, please let me know and we'll try to adjust. So thank you everyone for joining us today here in class and on Zoom. I'm glad to be invited by two associations here. We have ACI and ASC T&DI. So we're going to talk about 3D printing today. Okay, so a little bit on myself before starting. I'm from Montreal, Canada. That's why I have a weird accent. And I'm actually pursuing here a PhD in CE since 3 years. My research mainly focuses on concrete materials and pavement. So why 3D printing? Let's see if I can, whoops. Okay, so why 3D printing? Javier introduced it a little bit. So it all started with concrete, actually. With a sample here, I'll bring it in front of the camera. So a concrete sample, so super standard 4x8 concrete cylinder. I was trying to buy some caps to make sure that it doesn't dry for the 24 hours. And these caps are super expensive when you buy them from an external vendor. So I was wondering, can I 3D print these caps? And that's how I actually started 3D printing with these little caps here. So they make a really good job. They're reusable, better for the environment. I can change the colors depending on the mixtures I'm batching, and super quick to make also. I learned from tutorials, Googling, YouTube, super simple information, and it became to be useful for other tasks in my research and even a hobby. So I got a personal printer, the printer we can see here on the left. I am now sharing designs I made online with sharing platforms with many downloads. So I'm glad that it's being useful for other people. And just as a disclaimer, I'm not a 3D printer professional. I'm just doing that for fun. And I hope that you can learn from it and not make the same mistakes that I made. So I have a few learning objectives for you today. So at the end of the workshop, I hope that everyone is going to be able to learn what 3D printing is and how easy it is for everyone. Identify how 3D printing can be useful for yourself, for your own research, for your own hobbies. Find resources available on campus. There are plenty. So I want to share that with you. It's free. It's available to everyone as students. So why not using them? Also understand all the different steps that are required from your very own idea to the final object. I want you to gain basic skills on how to design an object, how to slice it, and how to print it. Find how it can benefit, how yourself can benefit to the community, or you can benefit from that 3D printing community. There's a huge amount of people online that are sharing their work, and you can also share to these people. I want you to avoid the most common mistakes that beginners usually do, that I did myself. Like we can see on this picture here, a huge blob of filament. It's a waste of material, waste of your time, and you cannot do anything with that, unfortunately. So let's avoid that. And I want you to see how 3D printings work. So, an image is worth 1,000 words. A video is worth 10,000 words. And then an actual demonstration is worth a million words. What is the structure of that workshop? So part one, I want to answer 10 popular questions that usually people have when they start 3D printing. We're gonna have a small break. I'm gonna do a demonstration of a few items I brought here today. Part three, we're gonna do a step-by-step guide on how to 3D print. So from your very own idea to an object, I'm gonna do a demonstration. And then if we have time at the end, a hands-on session with the printers. So part one, 10 popular questions that a lot of people have on 3D printing. So before starting anything, I want to know what your questions might be regarding 3D printing. So if you're here, it's because you might have an interest in 3D printing, but what are the questions you have? For anyone, even on Zoom, you can unmute yourself. Yes. Okay, so for people online that might not have heard, Lama is asking what kind of materials we can use and how the shape is being created. So we're going to answer that, hopefully. Any other questions? Yes? So cost, durability, these are going to be answered too. Any other questions? How long does it take? That's a super good question. Is it going to suit your need? Maybe, maybe not. So we're going to answer that too, time-wise. Yes? So how strong? Can I rely it mechanically on the part? Is it good in tension, in flexion, and compressive strength? We're going to answer that. Resolution, so accuracy, precision of a printer. That's going to be answered too. Any other last questions? How what? How big? What kind of printing volume can I print? So that's all going to be printed. Obviously, if it was that easy, we could print printers with printers and then do that inception-wise, and then. But unfortunately, it's not the case. So I decided to take 10 of the most popular questions, and I'm going to end them. If you still have questions during the meeting, please interrupt me, raise your hand, and I'll try to precise it. So first question, what is 3D printing? What is it? It's actually an additive manufacturing. So it is achieved by putting successive layers of material through 3 different axes. So let's say a normal printer is going to do only 2D, but when you stack multiple of these prints together, you end up with a 3D item. So that's what 3D printing is. A little bit of history. 1981 was the first patent. So it's pretty recent in the technology realm. 1988, first machine created. So we can see on the picture there, it's pretty old, but it still looks a little bit like what we have today. So it's recent, and technology is still to evolve a lot. And obviously it bloomed since the 80s with the emergence of the CAD tools. So it gives people a bit more tools. 2006, first available printer. It's recent, 2006. Before that, it was the industry, academia that would 3D print. 2009, the prints became public domain. And that's where it completely bloomed, where all different manufacturers started doing printers. So the cost reduced and the domestic market increased a lot. So people can buy printers for their home. In 2024, it's estimated to be a 40 billion market with a growth of 25% every year. It's huge, it's massive. 25% growth annually. It's a blooming market, so why not have technology for us? Question 2, what technology is available to us right now? The first one ever to be created is the SLA, stereolithography. It is using a liquid UV resin, and with laser, you can harden specific parts of that resin that is in a bath. So by having a Z-axis that is moving and a laser with a mirror that can direct the light wherever you want, you can harden the material exactly where you want and then move the Z-axis and build a 3D object with it. You have a smooth surface, there's high precision. Thing is, you can only have a small build volume, small parts. So I'd say 1 feet by 1 feet by 1 feet. If you go above that, you need to have professional printers that are super, super expensive. And still, a small machine is going to be expensive. Second technology that is pretty common is the SLS, where you use, instead of a UV resin, a metal powder, and you use a laser to fuse it. And then you can create really, really strong parts in metal, obviously. It is expensive, but the material itself, the powder, is pretty cheap. You can do complex geometries with that too. The third one is what we use today is the fuse deposition modeling, or sometimes called 3Fs, so triple F. It is a fused filament fabrication. It is consisting of an extrusion of a thermoplastic, and that plastic will cool down once you start printing it. So it's a pretty flexible material. That's what is being used for fused materials usually, and that you can print it, you can move it, but then if you actually apply it too much, it's going to break. So that's why it's important to have good geometries. You see, we can achieve breakage of these plastics. And by building a part, by fusing it and adding different layers, you can get a strong build, even if the material itself alone is not strong. And since it's the most common printing technology, we're going to use that for the rest of the workshop. Third question, why would you 3D print? Well, why would you do that? Why would you spend time, money, and effort to print stuff? So you can increase a lot your speed. If you do, for example, rapid prototyping, you can design, manufacture, test your part, and then do iterations of that part. So restart that cycle within even the same day. Say, anyone use the machine shop downstairs? No? Why? It takes 3 weeks, 4 weeks, a month, 2 months, 3 months to get your part. So let's say you want to do different iterations. You create a design for your research, your purpose, and then you test it. Oh, I need a little bit, change the shape and everything. You need another month after that. So with 3D printing, you can do that within even the same day. So that's a huge advantage of why people use 3D printers. You can reduce your costs a lot. Having a CNC machining tool, it's millions of dollars. You need advanced expertise to technicians to run that, maintenance and everything. So with a 3D printer, you can move it wherever you want. You can use it with almost unskilled people without breaking it. And you can use free designs online. So you can actually use stuff that people already put time on and use them for your own needs. There's higher flexibility. You can create your own design. You're not limited to a catalog. If you want to get, I don't know, something from Fisher Scientific, just to name, you need to select an item that is available in the catalog. Out of stock, you want to have a different color, you want to have different size. It's complicated. By making your own 3D print, you're not limited to that catalog of items. There's good accessibility. People with limited skills can rapidly print stuff, even from your own home, your own sofa. And it is somewhat sustainable. You can use plastics that are recyclable and even biodegradable. This PLA plastic here is biodegradable. So that's a good sustainable advantage. And there is less shipping volume too. Since you order a dense filament, you don't ship the full part itself. So this brain here, for example, that's printed is around 500 grams. So this kind of plastic is contained in a spool like that. So I'll show it to the camera. So this small spool here, so we can see that there's a reduced volume of plastic. So if you're to source from another country, then you kind of limit the shipping volume too. That's another advantage of 3D printing. I think Lama asked, what kind of materials can you print? So I showed the PLA. That is the most, I would say, popular amongst 3D printers. I would say hobbyists. The reason is that it's pretty cheap, $20 per kilogram. 1 kilogram spool is the biggest version. So the one we have installed in the printer, that size here. That's usually sold by 1 kilogram. It is safe, office friendly. It's not toxic, dangerous, or whatever. It is rapid. It has a low fusion temperature. So that's relative. let's say around 200 degrees Celsius. It's a printing advantage because you can print with normal printers at 200 degrees Celsius. It's not heating like to obtain, I don't know, sintering for bricks or whatever. It's pretty low, but that's going to mean that your item you're printing has a low thermal resistance. If you can print your material at 200 degrees Celsius, and once you reach 100 degrees Celsius, 150 degrees Celsius, your part's going to lose some mechanical properties. It's a thermoplastic. It's going to melt again. It's hygroscopic. Moisture is going to affect your part. So it's going to induce some volume change. Could be shrinkage, could be cracking like concrete. It is brittle when it's cold. It's not food safe. It is, however, biodegradable. So corn-based, many colors are available too. Clear, metal-like colors, glow in the dark. So that's all for PLA materials. It's available if you type PLA plastic on Amazon. We're gonna have thousands and thousands and thousands of results. So I showed a few material. ABS is also available, like Lego blocks. It's the cheapest of the materials. However, it releases toxic fumes when it's being printed. So that could be a drawback if you don't have a specific enclosure for your printer, good ventilation. If you do that in your basement, it might not be a good option to use ABS. It has higher printing temperature, 250 degrees Celsius. So if you need a part that is a little bit more thermally resistant, you can use that. It's not biodegradable, however. There's also PETG, which is FDA approved, biocompatible. So some people use it for any food-related items or even biological prosthetics, since it's biocompatible. It is strong. There's a higher cost, obviously, and it requires some experience to print it. So one last slide on, we have a question here.
Where can I buy these categories?
So we're asking where we can buy these categories. Anywhere basically where they sell, I would say, electronic equipment. So Granger, for example, .com have a bunch of different options. I'd say Amazon is a big market for 3D printing. You have a lot of different brands, different qualities. You can get super, super cheap filament. However, they might not be consistent in size, might jam in your computer, in your printer, sorry. Colors may vary too, temperatures. So, but usually Amazon is a good source for materials. If you use a specific brand, usually you can have an according quality to what you buy. So usually people go by brand. So once you selected a brand, it's usually guaranteeing a certain quality type, consistency, homogeneity. But if you really want to buy without looking at the name, you can look at the melting temperature, the density. Usually they give the accuracy of their size. So if you have a printer that's, I would say, doesn't have really good tolerance on filament size, then you might want to change brand or for a better filament. So that's usually, you have to check this basically size and consistency of your filament. Does it answer? Okay, perfect. CPU is, I would say, the second most used material. It's the famous cap I've showed you for the concrete sample. So it's a flexible material, super, super flexible. And we can use it for molds that we can easily demold after. I can show the small molds I've made with these small concrete Ouellet items. So it's made from a flexible plastic mold. So that is TPU. It has a medium melting temperature. It's pretty durable. It is expensive. The biggest drawback is printing time. You need a lot of time to print that material. Since it's flexible, once you put it, maybe I could turn the camera to the printers. Is it good on Zoom? Okay. So as we can see on the printer here, the filament is being fed to the printer through here, an extruder, a feeder. And the feeder pushes the material all the way to the extruder. That is that part that's mobile. So when you have a flexible material, that feeder here might have trouble pushing super fast the material. So it could buckle, it could get stuck in there. So to prevent that, you reduce the printing speed by, I would say, twice what you could do with normal PLA plastic. That's the biggest drawback. It's super flexible. Like it's the plastic I have here. So we can really like in super stretch, like elastic. So it's pretty strong. Like I can't see how like elastic this is. Let's put the camera here. Okay. Another is nylon. It's mostly used in the industry for its mechanical properties. It's a pain to print. It's super expensive, so you use it only for specific applications. Another cool stuff you can print is dissolvable filaments. So let's say you have a printer with 2 printing heads. You can print 2 filaments at the same time. You can print a temporary structure that you're going to dissolve afterwards. So for example, this bearing we can see here. I'll turn on pointer. We have some beads that are inside the bearing that we want to be perfectly printed and not touching the other surfaces. They're kind of floating in nowhere. To do that, we have to use a dissolvable filament. So based on what your printing material is, you're going to choose a different dissolvable material. So PVA, for example, dissolves in water, HIPS in hydrocarbons, and ABS in acetone. So you can have fake temporary structure hold and help you printing your parts. Last category is the specialty filament, stuff we don't really use but could be handy. Magnetic, so there's metal particles in it. Some that are conductive, you can print circuits with it. Some glow in the dark, textured, wood-like, stone-like. So this is all different materials you can use. Question 5, what are the limitations? If it's so perfect, why is it not used for everything, everywhere, at any time? There are actually limitations to 3D printing. Any ideas of what limitations could be? The size, that's a big, I think that's, no, it's not the first one. I would say the second one is the size. You're limited in terms of size. You cannot print big elements. So that's probably the biggest thing you can print, the last element here. That's something that if we put it on the printing bed, I'm sorry for the people, it's reaching the capacity of the print. I'll show. And that's for this printer. There are printers that can actually print bigger items. They're expensive. It's not something you can find anywhere, or I think the mechanical engineering department has a bigger one. I'm not sure of the volume exactly, but usually they're expensive to rent because, and the thing is, the bigger you go, the more compliance you have. So the more your frame is gonna get bended when you print. So then you usually lose a lot of accuracy once you go bigger. So if you want to, like a testing frame, for example, if you want to have bigger objects, you have to increase your frame size by a lot, and it costs you. The big drawback is the temperature resistance. If I take any element and I put it in the oven at 300 degrees Fahrenheit, usually what, I don't know, we cook food, it's going to melt. It's going to melt. You're going to lose your element. It's going to get all floppy and you lose complete mechanical strength. Printing size, Javier, smaller than 1 cubic foot. It's usually the rule of thumb. So 1 feet by 1 feet by 1 feet is usually for, I would say, types of printer. These here are 8 inches, 9 by 9 by 9. But I'd say rule of thumb, if you want a 3D print, make sure your print is smaller than 1 cubic foot. What you can do is multiple prints and assemble it afterwards. You have low mechanical properties. So since it's an addition of multiple layers, you have multiple planes of where you can get fracture. So where bonding could be not perfect. So then usually yield strength smaller than 10 megapascals. It's still good, it's still big. That's optimal conditions. If I print something super fast without having much experience, you can probably break it with your own hands. Inflection. Precision, pretty limited. I'd say smaller than 0.5 millimeter, you cannot reach that accuracy. So if you want really small details in your print, it's not something you can necessarily reach. Otherwise, you need to get smaller printers with smaller better accuracies, but it's still something that's difficult to get. Low speed. So I don't know if you saw it, but I think Sachin was here. I started the print here of the small eye 2 hours ago, and it's ready. Like it was ready 10 minutes ago. So it takes a lot of time, but good thing is you can do iteration super fast. But for production, it's not a good option. If you want to print a lot of the same size, what you can do is create a prototype with that and send it to a company that has a different process. Maybe plastic injection molds where you can get faster capacities. And you are limited in geometries. So that's, I would say, one of the big drawbacks. Let's say you want to print a sphere. So where's the small sphere? Let's say the Pokeball. If I want to print that, for example, and then I install on the bed, the area of contact with the bed is super, super small. And what that means is that when the extruder is going to apply the plastic, it's going to create some sort of a resistance. And then the part is going to unstick. And you're going to end up with a super blob like this of lost material. So what you need is to create artificial supports. So that's what we call supports. And it's what we see rotating on the image here. You need more plastic. You need more time. And after, you need time to remove all these small supports that are attached to your item. So that could be a problem if you're aiming for certain geometries. So let's say I want to print a brain. So this brain, to make it hold, I need to create a fake structure underneath to hold it. So this thing is discarded. This thing is lost plastic. But it's needed to make sure that when you print it, you actually have good stability and you don't end up with a big blob of filament. Question 6, where can you print? That's another good question. On campus, there are question before, yes.
I have a question for the previous slide. I agree with all of them, but let's say we want to measure the tensile strength of one of these odds. What about the defense? Like how much defense each box is assembled? Like for concrete, since it's real, we are supposed to test 5 vertical. What about the
That's a super good question. Usually 3D printing items are not used for final usage. Usually it's more for prototyping. You validate a design, the shape, all that. And if you want to have a stronger part, what you can do is you do a mold out of your part, and then you use a material that's stronger. However, I printed some hooks to hold like plants from the ceiling, and I didn't test it in tension, but I pulled on it the strongest I could, and it didn't break. And I would say the size of the shaft was, I'd say 1 centimeter diameter, so 10 millimeters. So it's pretty strong, but if you have one layer that didn't work well, then you're done. I would say that since it's super cheap to produce, you produce 20 of them, and then you test them and use the one that's the strongest. So that could be a way to kind of go around that, but I wouldn't rely the civil engineer, for example, on a 3D printed element without good quality control, quality assurance testing, and whatever. You can always change the parameter to print it with, so let's say you design an item, what's inside you can decide to put full of filament, or then there's a certain infill that's 10% of the area is filled, or 50% is filled. So by playing with these parameters, you can, let's say, have better mechanical properties. But I don't know, professionally wise, I haven't used any items, structurally speaking. But I would say if concrete is 5 and it's still a heterogeneous material, for 3D printing, I would say maybe 10 or 15, you know, and then you choose the one that you do a half test capacity, like you do for anchors or this kind of stuff. So question 6, where can you print? There's a lot of resources on campus. The IDEA Lab and Grant Library is one of these. They have printing services. So you send them online your design, and they will slice it, they will print it with a pretty short lead time. There's the Illinois Maker Lab, and this one is more of a lab where you can yourself go have classes on 3D printing. They can assist you on your designs, and then you can print it yourself on a printer. So that's kind of a good advantage. It's cheaper if you do it yourself. It's still pretty expensive. There's the Fab Lab. There's printers in the Art Plus Design Innovation Studio, MEC SE, and in the ECE department too. So almost all departments have 3D printers. We don't have any in the machine shop in the CE department, but a lot of research group have printers. So maybe if you have a colleague, you can ask them and you can print it for you or give you support. But there's nothing official as of now in the CE department. You can print at home or in your own office if you have a printer. Your local community is here also with you. In Urbana, in the Lincoln Square Mall, there's the Makerspace. So you can go there. I don't know for COVID, but before you can go there and they have volunteers that are there to help you, and they have a few printers. Some Staples and UPS stores also accept 3D printing files. I don't know how long in terms of lead times they have for printing it. So we have a Staple here in Champaign, but I'm not sure if they're offering 3D printing. And online, obviously. However, if you send a file to an online service, maybe out of the country, it could be useful if you want specific materials like specialty stuff, big volume size, but don't send that for normal printing stuff. It's going to cost you a lot of money. Shipping, I wouldn't recommend it unless you really need something specific and pay for it. Question 7, how much is 3D printing? I think Egemen asked that. How much does it cost? Is it expensive? Is it cheap? If you print on campus, for example, how usually they charge is they charge per gram. And they have some installment fees over that. So the bigger you print, the more weight you have, the more expensive it's going to cost. So 10 cents per gram plus $4 in the case of the Idea Lab. Maker Lab is $15 per gram plus 20% if you let them do it themselves. So that's what we have on campus. So to give you just an idea of how much stuff is weighing. So let's get this Illinois here. So how much do you think it weighs? Okay. 100 grams? So that would be $10. Let's check it. 171. 171 grams. So $17 just to print that. It's not cheap. There's stuff, and this one is empty inside. It's an empty, almost an empty shell. It's a small structure, but it goes. So let's say this Lord of the Ring bracelet here, 25 grams. It turns out pretty expensive for small items that you might not really need. But for research, let's say you want to have a cap. This cap, let's see, I've reused them probably 20 times. So 30 grams, $3. And if you go on, I don't know, Gilson, you can buy them and they're single use, super cheap, and it's probably what's going to cost you for one. So that could be a good advantage. Let's say you want to print home. You need to print a lot of stuff. Entry-level printers, usually 200 to 500. So what we have here is a $300 printer, but it comes in parts. You have to assemble it yourself. The filament itself, one big spool like that here, full of material. Rule of thumb, $20 for PLA plastic. That's 2 cents per gram. Power consumption of a printer, 5 cents per hour-ish. So let's say you have a $300 printer. You need to print over 8 kilograms of material to get your money back. So that's 8 spools. To give you an idea, this one here is half a spool. So you don't need to print a lot to get back your money if you get a printer. Let's say as a research group, for example. There are some tools online where you can calculate the cost based on the power consumption, your material, the weight, and everything. Could be pretty handy. How much does it cost online? Thing you have to pay for the shipping at first. It could be big parts. There's a long turnaround time. And some companies, they will charge by the overall volume. So let's say you take the outer measurement and they're going to charge a specific price per cubic centimeter, for example. Other websites, you just do a quote. You send your item and they email you in a few days saying that, oh, I'm charging you $57 plus shipping for that. What equipment do you need? Question 8. So let's say you want to buy a printer. If you were to buy a printer, what do you have to look at? We have here in front is these printers here, the Creality Ender 3 Pro. They're at $260 right now, plus a $15 coupon on Amazon. It's super cheap. I've been using that for 3 years. Knocking on wood, never broke. I've been printing, I would say 25 kilograms, 30 kilograms total, and it's still running well. So they're good printers. Look at the ratings. Usually that helps. If you want to have the Cadillac of printers, the Ultimaker is good machines, wireless. They have a camera inside. It's super nice printers, but we're thinking of $3,000, $4,000, $5,000, $6,000 per printer. What to evaluate? What kind of feature do you want? Print volume is important. What size do I need to print? What temperature is the extruder going? Is the bed itself heating? That's important to prevent thermal gradient between the extruder and your part itself. The accuracy, is it UL certified? If it catches on fire and you burn your whole lab and your insurance is telling you, I'm not covering you because you bought something really bad from internet and it's not UL certified, I'm not paying you back. That could be a problem. Make sure it's UL certified. Is it pre-assembled or not? These printers, they come in a box that's big like that, like almost 2 shoe boxes. I spend the first one maybe 5 hours assembling it. For some people, it could be a problem. If not, buy pre-assembled, you're going to save a lot of money. Buy not pre-assembled. Some printers have a power outage feature. It could seem, I mean, not useful, but you're in the middle of a print, power out, then you have to restart your whole print. So some printers have this function. Some others have a filament sensor. So if you're printing and then your printer is running out of filament, for example, the brain here, I got a spool that was already used, and then close to the end, I ran out of filament. So it's kind of cool because we can see inside. But if it was a professional print, then I have to throw it away because I ran out of filament. So that's some printers, these do not have that feature, but some printers have a sensor. And then once your filament is running out, it's pausing, and then you feed another filament. Some printers have double extruders. Some have online print features. You can be home, you print in your office, there's a camera, you monitor that. We're talking about the Ultimaker here. And also the bed auto leveling, that's super important. If we look at the printer on the left, there's a mechanical dial on it that I installed. This is to make sure that the bed is fully leveled with the extruder. So if you don't have a perfect leveling, by saying perfect is 50 microns difference, what's going to happen is your part is not going to stick well to the surface. It might unstick, and then you end up with the big blob of filament that you have, something you not necessarily want to. So if you want to buy a printer, that's what I would recommend to check first for avoiding any problems and making sure that your printer is fitting your needs. Question 9, how fast can we print? So Sachin, to answer your question, how fast can you print? On campus, usually 2 to 3 days as a turnover time. They print for you, but obviously you have to pay for that. Online, 2 to 3 days to ship, plus the printing time, 1 to 2 days maybe, so maybe a week. At home, it varies a lot. So as we can see on the figure on the right, depending on the geometry of your shape, you're going to change a lot your printing time. So since it's an addition of different layers, if you have an object that's more oriented towards the z-axis, the height, you're going to need a lot more layers. And what a layer implies is that you put your whole thing, and then you repeat it on the next level, print the whole thing, and then get another level and print the whole thing. And you do that and stack all your sample all the way to the top. If, for example, you take that sample, that object here, and you lay it down, then you reduce the number of layers. And just by changing the geometry of your item, you can cut down by half your printing time for the same exact object. Also, if you have a full part or a part that's partial, then you have to think that the printer has to do all the contouring, and then it stops printing, so retracts the filament, moves, and then feeds the filament, and then print it. So all of these successive steps are adding some time on your printing time. Also, if you want to have an empty shell or a full shell, it's going to influence how much plastic and time you need to print your part. Rule of thumb, I'd say if you have a simple part that's rather simple, I don't know if I have an example of, let's say the me Lord of the Ring here, ring. That's probably 30 minutes. Pretty quick. If you want to have a big part like the brain here, it was on for 4 days. It was the downstairs in the lab. You probably heard it, right? So it's in the cement chemistry lab downstairs. It ran for probably 4 days. So it's super complicated, intricate, a lot of layers and details on the brain I can show for people on Zoom. So it's actually a real brain from a guy that did an MRI and asked for the digital file. And what he did is he made it available online so people can download it and print it. So that's a real size brain of a person that's living here on planet Earth. That's pretty cool. So, yeah. Yeah. Yep. So what I did is I installed a camera. So these printers don't have cameras on them, but I installed a network camera. So then you have to monitor and make sure that there's no problem. So for example, the filament that now it was close to the end, and I'm like, okay, everything's going good. There's no problem so far. There's like 2 hours left to print. I won't monitor it, but that's where all the problem happened. So it's good to monitor, go once in a while. Since it's heating, it's kind of safer to monitor it for fire hazard or whatnot. But some of the problems that could occur is a jam of filament, is running out of filament, is a blockage of some sort, or power outage, for example. So that's all problems that could happen. And any other questions? Yes. I would say it's like concrete or any other material. If you have a construction joint, then it's going to be difficult to get some sort of adhesion on that surface that's been hardened for quite some time. You could use, what I could do is print. So that's what I'm thinking of doing with that, is actually printing just the top and glue it on it. So this one, why it took so much time is that it's flexible filament. So as we can see, it's really, really flexible because I wanted to have like a real brain feel on it. So it took more time to print for that reason, but just printing the cap on it wouldn't take too much time. And then I could just glue on it, but if you want to put it, the thing is that you really need to position it in a very, very, very precise location so that the printer starts there. If you're offset just by a little bit, then you're going to have a blob of filament that's extruding in the void. So that's why maybe it's worth spending a little bit more on a printer that has that filament option. These have the power out, and it's been handy a few times. Last question, what skills do I need? So you need to print, you need to buy a printer, or you need to, for whatever reason, use some 3D printing. What kind of skills do you need? None, actually. Absolutely no skills required. Reason is you can find a design online that someone made. You can send it to a place where they can print it for you, and you just go pick it up, or they can ship it for you. So you don't need any skills at all unless in a computer and knowing how to use Google. However, you're limited in designs from what you find online. Could be costly, time consuming, and you might need a few iterations to get a good design. If you have 2D CAD examples, it's pretty much the case for all civil engineers. They know AutoCAD, for example. Or if you have played The Sims or Minecraft or whatever, you have some idea of 3D orientation, it's going to be super easy for you to pick it up. Now slicing, that's where you tell the printer what exactly to print. You need a specific software for that. So if you send your part for external printing, let's say at the IDEA lab here in Granger, you don't need to know how to slice. They do that for you. However, if you have a printer or you want to print yourself at the Maker's Lab, you need to know how to slice. So I'll try to show that a little bit later in the workshop. The printing itself is the easiest part. You upload your file, your code inside the machine. It's actually a text code of all the coordinates of where the printer needs to go. And you press play and it prints. And hopefully you did a good design, it doesn't crash or fail. But that's the easiest part of all 3D printing, the print itself. So that ends the first part of the workshop, the 10 most popular questions. Do you have any other remaining questions you might have on 3D printing? So we asked in class on how to select the infill percentage. We will cover that a little bit later in the step-to-step manual if you want. But it all depends on the time you have for printing and the kind of mechanical strength you need in your part. So I have a few examples here of different infills. So I don't know if I can probably show. For some reason, it doesn't want USB camera. So I'll show that. If some people want to take a break, it's a good time. You can take a look at the parts here. You can take, let's say, what, 5-minute breaks maybe? Less than that? 5 minutes? Okay, 5-minute break. So as we can see, is it good on Zoom? Yeah. We have different types of infills. So in that case here, that's 5% infill to all the way to the top, 100% infill. So we can see that at this value here of infill, which is 50%, we get pretty much good mechanical strength for parts. But obviously you increase a lot your printing time. So that's what kind of different infills you can use, different designs, geometric shapes, or percentage of infill. So how to select it? I would say it's iterations. You do a design, you test it, you select another infill, and then that way you can select a good infill. Okay, we're going to resume the session. Let me share my screen. Share. Do we have any questions before jumping in part 3, the step-by-step guide? No? Okay. 3 major steps are required to go from an idea to an object. First one, you need to have an object design. You have to have a 3D model digitally of what you want to print. You can download that from external sources. That could be any people that design it for you, or actually some free sharing softwares, not softwares, websites. You can scan it as well with 3D scanners. So if you have an object you want to copy, a special part you cannot find anymore, you can scan it and have a digital file. And the last option is to draw with a CAD system your part. Let me close that Zoom window. Okay, second step, you need to slice your object. So what that means is you need to configure the printer itself and tell the printer, I have an object, you need to do that many slices, that many print, and then you go higher in the print. You need to tell the printer all these steps, and that's what's called slicing your object. So you go from a design file, you import that into this, the slicing software, and then you can finally here print your object with a printer. So it's pretty straightforward to print. However, you need to do critical adjustments before being able to print. So these are the 3 major steps I'm going to go through during this step-by-step guide. So first, object design. You can have you can obtain a design from an external source. There are plenty of websites. What you want to look for is an STL file. You can maybe find some J file. So for object and stereolithography, STL. So these are the most common 3D object file you can find online. There are plenty of free galleries. One a good example is Thingiverse. However, you really need to make sure that you have a good design, because a lot of people put a lot of crap up there, and then you spend a day printing your element and you realize, oh, it's too small, oh, it's too big, oh, this, oh, and that. So it's very important to choose a good design. And then sometimes it could be limited in copyright. Some people put stuff, including myself, and you put a license for non-commercial use on it. So if you use it for academic purpose, I don't know how that works exactly, but if you make money or you patent something and you use one of the part, you could get sued and you could have problems afterwards. So make sure when you use a part, it's free of any copyrights. So look, let's go take a look on Thingiverse. I don't know if I can click on that. Let's use backup plan. So Thingiverse. And let's say we're looking for Illinois logo. So there's a bunch of crap, right? So you see there's even the NIU thing. There's some competition there, NASA stuff, some ads. Okay, there's a night light, Illinois style. That's pretty cool. Oh, there's a block logo. So for example, here you have a file. It looks good, right? Well designed, nice item. And you have the file itself there. So what do? You download the file. There's some obviously directed advertisement. You see, license, super important. So desktop, save the file. And here, there's a bunch of license information. So you can find some information on it, the person, how they printed it, in fill and everything. But you want to go use Illinois logo. When you open that file, there's a README where you can find license as well. So that's super important to check. And then you have your STL file here. So that's what you're looking for, STL file. That's from Thingiverse, as easy as that. You can type whatever you want. If you want not safe for work stuff, you need to activate an option, just saying. But there's absolutely everything you want on that website. There's some paying galleries as well. You can pay and get some items that are professionally done. You can have some online design services. For example, CAD Crowd, you send a design and people bet on how much they make that design for you. The advantage is they could do, geez, what's the name for that? FDM on it. They could do fluid dynamics analysis. So they can really optimize your part by mechanical engineers and have the lightest item possible with the biggest strength. So that's some stuff you could do with external sources. Now, what you can do as well is draw it yourself. 3D CAD, pretty straightforward. You need skills, time consuming. Some software, SketchUp, maybe some people use it to design your home or whatever. There's a trial mode, but it's kind of expensive if you want to use it more. There's Autodesk Fusion 360, free for students, super, super popular in the 3D engineering world, 3D printing world, sorry. There's, of course, if you want to use professional licenses that, for example, we have on campus, you can use CADIA, SolidWorks, Revit. They could be complicated to learn at first, but they have a lot of features. So you can model your 3D part directly in these programs and say, okay, if I apply a stress there and a stress over there, you can use with some material properties that you have to input or find online. You can model where the stresses are concentrated and optimize your part that way. So demonstration, let's see, for example, Fusion 360. So here's that Fusion 360. That's the design I made itself. So it's the Illinois. What I did is I got the logo online in vectorial format. I extruded the design itself. I applied some fillets and chamfers, and you have your design. That's it, that's all. So that's Fusion 360. Yes?
How do you design this logo? Like, do you use vinyl or leather?
I used the vectorial file that the U of I has directly from their graphic website, where you can get all these branding information, including colors and everything. So it's what we can see in yellow under. It's that design there. So you can import logos, you can import 2D stuff and extrude it afterwards in that software. So that's for Fusion 360. You can use some softwares that are on the cloud. So let's say you have a computer that's not too performant. You want to use your tablet, or you have limited functionality. You can use these cloud softwares like Tinkercad, for example. It's free. It's super easy, but obviously functionality is limited. There are even iPad apps you can use to 3D design stuff. Super cool. You have a stylus design your stuff. So it's just a matter of suiting your needs. What kind of level of, if you want to do a thread, for example, like this air compressor filter, here there's a thread on it. You can actually put it there and screw. You kind of need to have usually advanced software to be able to do that. So this thread here, I don't remember what's the metric thread that I couldn't find. Let's say here the container. I'll go in front of the camera. So that's a container for a calibration weight here. So I designed it with a thread here. So that's all 3D printed. So if you have custom parts, it's usually useful to have a powerful software to be able to have some freedom. And there's even text on it. You probably cannot see it, but it's like personalized information on it. That's cool stuff you can do. Third option is 3D scan an object you already have. So here there's a 3D scanner, handheld scanner. So what it does is projects and with infrared light a pattern, like a grid, and then there's an infrared camera that reads this pattern, and then with a depth sensor, it is able to measure directly in 3D the part. So what's cool is you can digitalize pretty much anything. So this is called structured light, this kind of scanners. Face ID on your iPhone is using that exact same principle to scan your face and unlock if it's really you. It's quick, no skills required. It's extremely expensive, $500 a thing. You can rent it. That's from the IDEA Lab in Granger. They have lockers. You go online, you reserve it, they put it in a locker, they give you the code. You have it for 2 weeks, 3 weeks, and you return it back after for free. So that's what IDEA Lab can do for you. So I'll show you if Windows wants to cooperate. So unfortunately, this is a really old scanner and it only works on Windows. So while this is restarting, I'll continue on there. You can use phone apps. Directly the camera converts that to point cloud. True depth camera, that's the structured light and you have on your face ID recognition, and LiDAR scanners. So new iPhones have LiDAR scanners. So you can actually scan big volumes super quickly with that. You can transfer that into STL files, and you can use that as a 3D file directly. Okay, let's see if it wants to connect. So I wanted to demonstrate. Maybe Javier, you could walk over and I'll show you how you can scan if it wants to cooperate. You're going to 3D print a trophy with Javier on it. Well, maybe you won't have to pose it all because it says device not connected. So I'll unhandle, okay? It's completely as you want. And I might use that scan against your will. Okay, so that's the software. This product is being discontinued and it's still being sold for $500. So we have a person, full body or head? Let's say head for the, okay. So, no, let's keep your mask on. Okay, just for, okay. So really important, you don't move. 3, 2, 1. Okay. Stand still. So now what it's doing is it's acquiring a bunch of a multitude of points, and then slowly by moving, and then you do the complete shape of that. Pretty quick. Let's get the hair. Okay. Pause the scan. Let's use that for now. It's exhausting, right?
Yeah.
Creating
I
model.
don't know how real.
So now we have Javier in 3D here.
Oh,
And then you can solidify. What it does is it fills all the voids, and then you export that in an STL, and I could print that in, if it's small enough, in an hour, and you have a mini Javier. So let's solidify that. I want to show you for the principle of it.
I'm gonna be selling statues of myself for $1,000.
So now you see, you have the bust, and then you have a Javier in 3D. So that's what 3D scanning can do for you. So if you have a part, for example, that's not, I rent a 1932 house, and it has some old like faucet with the ceramic handles, and I couldn't find that anywhere unless I pay $100 to fit that exact faucet thing. I scanned it and I 3D printed it. So I have a example here. I have a faucet handle. I made a red and a blue one for hot and cold. That's stuff you can do when you cannot find a part and you want to replicate something and not spend hours and hours to design it. Second step, you want to slice your object. So you need to convert your object volume into a printable steps. It's critical to have a good balance between speed and quality. You need a software. Ultimaker Cura is one of the most popular. It's free for students. It has a huge library of different printers. What's important is that you put into that software different information that's applicable to what you're going to do. For example, the printers we have, that's for the Creality Ender 3 Pro. You need to input that into your slicing software so they know how much can I print, what kind of resolution, what temperature, and all of that. What are the steps? You need to import an STL file. So what we got from Thingiverse, the .stl, now you import it into Cura. Let's do that. We have Cura here. So let's put that full screen. So that's Cura here. What you need to do, let me see if I can hide. You have a prepare option. That's what's going to show up when you open. You select your printer. You select your nozzle size, your material, PLA. Put that back there. After you select a bunch of printing settings that I'm going to go through quickly. Let's say, for example, we print it like we obtained it from Thingiverse. So when I designed it, I designed the part exactly like that. Upward. Remember, for the printing time, when we have something that's upward, it takes a lot more time to print. Now it's slicing with a low quality setting. So I'm just using what Cura is providing me. 4 hours, 50 minutes to print that little Illinois thing. We can simulate what we have. And now we know, oh, here there's going to be some infill, partial infill. The blue stuff is supports and so on. 68 grams, $1.28. So that's simulating everything. The supports is the blue stuff we see. So to be able, for example, to print that, this thing you cannot print in the void. The filament won't be supported. That's the blue structure we see on the wall. However, if you put it that way, you don't need support. It might be pretty fast. So if I do that real quick. Yes, like this, for example. This one here. It's a structure, and if you look, there's a bunch of mini squares. So it's a hollow, like super compressible structure. It's almost nothing, just enough to support your part. This one, an hour 54, cut down in half the printing time, 24 grams, 3 times less plastic, just by adjusting the good geometry. So, what's that? I didn't hear you. Let's slice, yeah. Let's do that in an advanced workshop. Second step, you need to select the printer, select the filament, select the printing settings, and that's where it gets tricky. So now I've just used the random stuff that Kira is suggesting me. You simulate the print and you evaluate how much time, how much plastic do I need, and that's pretty much it for slicing. However, if you want to become better at 3D printing and have optimal parts, you need to simulate many times to optimize time, weight, and strength. So like we saw, you can simulate the printing. So you see exactly where the nozzle goes, how fast it goes, and then you can estimate time and whatever. So what's important is that to understand these settings and then run a simulation, adjust settings, run a simulation, and do that as many times as you need to optimize the parameter that's important for you. The most important setting is the layer height. So for example, this one has 4 layers, high height. This one has multiple layers with a smaller height. This one's going to take a lot of time. However, this one is the contact area between the different layers. And this one is the contact area. So we see for the same nozzle size, this one's going to be much stronger. It's going to take obviously more time. So that's how the layer thickness is going to influence. Usually 0.1 millimeter is the lowest you can go, and 0.6 is the highest. So you have to play with that, depending on your material. So if you need more details, you can always go look at that presentation on the internet. Second thing is the wall count, the number of wall skins you add on your item. So that's another setting you can specify. You want 2 walls, 3 walls, 4 walls, 5 walls, and then all the rest inside is infill. So you have to specify that as well. The top bottom layer count. Let's say when I print, for example, this super elephant here, that is a utensil strainer when you do your dishes. It leaks by the trunk, super cool. If you don't put enough bottom layers, then water is going to go through. So you want to have at least 6, 7, 8 bottom layers of materials, not a void structure inside to have a better waterproofing. So you need to specify these layers as well. What's super important as well, the infill setting. So you can specify 100% to have a solid item. We cannot probably see on the projector maybe. You see this one is this empty shell, 2 hours, 44 minutes, 22 grams. This one, 3 hours, 32, but just 37 grams. So 32 versus 37 grams. You don't use a lot of plastic, but you get a lot more rigidity. It's like a truss design, for example, for a building. By using the right material at the right place, you can improve a lot strength without using much material. So that's what infill is doing. If you have big structures like that, for example, you want to have a lower percentage of infill, obviously to reduce cost and weight, all while maintaining good strength. That's what's the priority in there. There are different patterns, like I showed during the break. It is required to have infill for objects with a horizontal top. For example, this one here. I have a support to hold the bottom of it. But then what's going to support the top if I have infill? You need to have a structure inside to support that final layer up there. So that's why infill might be. Usually 20% cubic is the way to start. 35% gyroid for better strength. And that's all stuff you can figure it in Cura. Skin overlap as well could be important for good bonding when you use TPU for molds. That's all settings. The printing speed, you can tell the printer how fast you move your nozzle. So follow the filament recommendations. It can be changed depending on what you print. That's some recommendations I have for the first layer, outer wall, top bottom layers, and infill. And then you can refine that by clicking on the small eye. It took me some time to figure that out. And you see from all my time, there's an hour 43 for the inner walls, an hour 6 for the infill, It tells you what percentage of your filament is being used for that purpose. That could be good if you want to refine a design. Supports, like I showed, like Javier asked, it's a temporary structure. We see in blue there. You can dissolve it if you use proper filaments, but usually it's just a structure you remove from the part afterwards. It helps for good stability if you print a sphere, for example. 45 degrees is usually a safe value to put support. So if you have a overhanging part at 45 degrees and above or lower, you want to have supports to hold that up. They're complicated to move. Ideally, you want to eliminate it, like I showed, by having a good placement on your bed. Something you want to make sure is have a good bed adhesion. You will have different types of settings to make sure that that happens by printing, for example, a brim around your part. So let's say I'm printing this part here, the Super Game of Thrones. If I'm just printing like that, there's probably going to be blocking of that disc there. So what I want to do is print a few extra layers around it, just to make it stick more. That's something I'm going to remove out. Well, that's called a brim to provide good bed adhesion. Material retraction. If you print flexible filament, if you have one thing to remember is to disable the retraction of the filament. So remember, when the nozzle moves to another printing location, it retracts the filament. You stop printing. But if you allow that for flexible material, it's going to jam for sure in your feeder. So you pull, it's super elastic, but you stop. You push and push the filament. There's so much delay that it's going to jam your printer. So it's going to make some hair. If you look on the brain afterwards, you're going to see some mini hair, like that's from the nozzle movement. But it's required for TPU. Finally, temperature. Follow what the manufacturer is telling you, and that's going to help you. Finally, when you finish your design, you want to run a simulation and see through your sample, slice it. Is it good everywhere? You can run it again if it's letting me. So we see that's the building we have on the quad. You run a simulation and you see through the sample how it looks. Optimize if necessary. If everything is good, you export your design in a G-code file. So you go from STL to G-code, and what it is, it's a text file telling your printer you go at that temperature. You print that coordinate first at that layer, and then it tells all the settings to your parameter. That's something you can edit if you're pretty good, but usually it's something you don't even see. Final step, one slide, printer setup. You want to preheat the extruder in the bed. So the reason is that once you fill filament for the first time, you want to have a hot nozzle so you can extrude the filament that was used before. So you push on it, and there's a manual knob on the printer. So you can see here. So this knob here is controlling manually the filament. So you want to push and remove that to extrude all the rest of your material. So that's why you have to preheat. You want to level the bed. What I mentioned to you is critical. If you have one thing to do with your printer is make sure it's well leveled. So you have 4 wheels on the printer. These are to adjust the bed, like a scale, for example, when you adjust it. If you're too high, you have some bonding issues. If you're too low, you're scraping your bed. So you want to be just perfect to promote good adhesion. Something that could help you, use an alcohol spray. Like rubbing alcohol, you spray it on your bed, and after you wipe it, it's going to remove all the maybe fatty residues you have from your fingers, like oils, and it's going to prevent good adhesion. It removes the dust, removes any foreign contaminants on your bed. So it's super simple, spray and wipe. You load the filament in the extruder. So you take your filament, you put it in the printer. I can show you that at the end of the workshop. You start the print, and then you monitor. You have to check if the leveling is good. Once you check in front here, I'll go fast because we have only a few minutes left. but I'll show you. I close the video on the smaller camera. You see that I printed a skirt around the item. So a skirt is that unbonded, see that? Unbonded element around the item. The only purpose of that is to make sure your bed is level. So the first thing that's being printed is that small item around it. If your bed leveling is perfect, you're going to have a consistent skirt around the element. That's how you make sure you're really well leveled. So once you make sure your bed is level, the print is good to go. When it's done, you remove the object. Some printers, like this, for example, have a magnetic bed. I would suggest you that. How you remove the part? It's super, super easy. When you have a glass bed, usually you need a scraper like that. And you need a pretty complicated. So magnetic beds are wonderful. I changed the bed on mine after a year and a half. So this one is almost new. So this is a good thing of these magnetic beds. Once you're done, remove the filament from your machine. Remember, it's hygroscopic. If you leave it out there, it's going to become super, super brittle. So you want to put it in a bag with some desiccant, stuff you have in your shoebox that says do not eat. Put that in a bag, in a plastic Ziploc bag, and then humidity won't get through your filament. So that ends the how-to guide to 3D printing. If some people want to stay, we could have some hands-on demonstration with the printers. You have any questions? No questions? Yes? How I move the what? So how you remove the base, you can use some pliers and to rip and cut that material. You can use a sanding paper. You can use these rotating Dremel tools to remove the brim that you might have printed around it. Same thing for the supports. Usually pliers are useful. You can heat them a little bit with a torch, a heating gun, or even a soldering iron, and then you melt where you want to remove your support. So these are all options you can do. Any other questions? No? Perfect. Well, thank you for your attention. And if you have any questions, you can come in front and I'll show the printers. Thank you.